Section 2.4. This is math. What is it? Math 204? Yeah. And other associated things. We're going to look at sequences and series. We know what a limit is. We know what a continuous function is. We know what polynomials are. Now we're going to consider sequences and series, which are kind of related to these sorts of things. And these are really important. You've seen them again and again and again. And there's a reason for that, of course. And that, as it turns out, is because they're surprisingly important. Right. You kind of know what a sequence and a series is already. Too bad. I'm going to define them. A sequence. S, K, K an element of n, and I'm going to sometimes just write this as SK, and sometimes just to emphasize it, if necessary, I'll put the K in. I won't always put it's inside the natural numbers of complex numbers. So sequence of complex numbers is a function S from the natural numbers into the complex numbers, where S of k equals S little k. Some examples. The sequence ik, which is equal to I minus 1 minus I, 1, I, so on. Sequence 1 plus I over k, k squared plus 1. 1 plus k 2, 2i 5 minus 2 plus 2i over 10, so on. And every real sequence is, of course, a complex sequence. Definition. A sequence converges to a number inside the complex numbers if and only if, for all epsilon greater than 0, there exists a natural number. So that for all k greater than or equal to the natural number, sk minus l less than epsilon. We write this as, there's a combination of ways to write this. Sk goes to L, as k goes to infinity, and the limit k goes to infinity of sk equals L. As a little side point, if you know about topology, n with its topology and standard definition of continuous limits convergence gives this definition here. So this definition looks different from the definition for convergence that we had for functions. It's actually exactly the same thing, of course, because S can be considered to be a function, except you need to know what the topology is on the natural numbers. And one way to write that down is this. For the particular class, Math204, you don't need to know about all of that, but just for those people who do know about topologies, there's a little bit more going on in the background. And this stuff is actually all, in some sense, standardized and the same. It's not a weird brand new definition. Sorry, just organizing my notes. Right, continuing the previous definition, a sequence that converges to a limit is called convergent, surprisingly. Otherwise, it is divergent. if the limit sk goes to infinity of s of k equals infinity, you have to work out what this means. Then sk is said to diverge to infinity. Examples. Is divergent. Why? If it's convergent, the distance between any of the points in the sequence must eventually be getting smaller. That's what that definition about the epsilon and so on means. They have to be they have to be getting closer and closer to the limit point, and that means they have to be getting closer and closer to each other by the triangle inequality. So, if the distance between them is constant or increasing, it has to be divergent. And well, that's 1. What's that? Which implies this is divergent. Or maybe another way to put it is, if sk is an element of d epsilon z, then sk plus 1 is not an element of d epsilon z for epsilon smaller than square root 2. Let's say square root 2/2, just to be safe. Ik over k. This is the sequence given by I minus 1 over 2 minus I over 3, 1 over 4. Converges to 0, and you can prove this. Ik over k minus 0 equals Ik over k equals 1 over k, which goes to 0. Boom, done. And you can check. Let's do it. It's important to see the definitions written out properly. So choose epsilon greater than 0. Pick n, so the natural numbers, so that 1 over n is less than epsilon. Then Ik over k minus 0, which is 1 over k, less than 1 over n, less than, for all k greater than n. K greater than n implies 1 over n is greater than 1 over k, which gives us the result. Right, there are other examples in the notes. You should go check them out. I'm just going to go on with proving theorems. I love proving theorems. Oh boy, here I go proving theorems all over again. This is let sk be a complex sequence, and suppose sk is equal to xk plus iyk, with xk and yk element of the real numbers for all k. Then the limit of sk, the limit sk goes to infinity of sk is equal to L equal to u plus iv. Right, L is a complex number, so it has to be equal. There are always a u and a v that will be equal to L. If and only if the limit sk goes to infinity of xk equals u and the limit sk goes to infinity of yk equals v as real sequences. Now you've seen this before because you've proved the same thing but for functions. And remember, a sequence is a function but with the topology associated on the natural numbers rather than the complex numbers. So this result actually follows from almost the same proof. But it is worth seeing the whole thing actually proven using the proper definitions, because that will help you learn the definitions maybe. Right, okay, now let's suppose sk converges to L. Then, for all epsilon greater than 0, there exists n an element of natural numbers, so that k bigger than n implies sk minus L is less than epsilon. Since xk minus u is less than sk minus L, less than epsilon, and yk minus v is less than sk minus L is less than epsilon, we know that xk converges to u and yk converges to v. How do I know that? Write down the definition of convergence in the real numbers. Suppose xk converges to u and yk converges to v. Then, for all epsilon greater than 0, exists a natural number, so that k bigger than the natural number implies that xk minus u is less than, and I'm changing the epsilon here. I'm going to say half. I can do this because it's for any epsilon. But I want to write down epsilon over half here because I'm thinking of picking a particular epsilon. Picking any particular epsilon. And yk minus v is less than epsilon over half. Then sk minus L, which is equal to xk plus iyk minus u plus iv, is less than or equal to xk minus u plus yk minus v, which is equal to epsilon over half plus epsilon over half, which is equal to epsilon. Oh, I'm done with the proof. Again, not so surprising because you've seen it before for functions and limits of functions. Sequences are functions. And here we have another result that's very similar to what you've seen before. If sk converges to L and tk converges to m are two convergent complex sequences, then 1. For all alpha inside the complex numbers, alpha sk converges to alpha L. 2. sk plus or minus tk converges to L plus or minus m. 3. sk times tk converges to L times m. And 4. Provided that m is not equal to 0 then sk over tk converges to L over M. Example. You should prove this. You can prove this in the same way that you've proven it for convergence for functions, just with a slightly different definition. It is worth doing. Please do it. It will really help your understanding. Why are my right-hand brackets always better than my left-hand brackets? See, even that's not a particularly nice bracket. Over z, 1 over z squared, 1 over z. Is convergent if if the modulus of 1 is less than 0, then this thing is getting closer and closer to 0, and the whole thing is converging to 1. So another way to see that is that the limit as k goes to infinity, 1 over z k over 1 over z is equal to the limit of 1, k goes to infinity, minus the limit as k goes to infinity of z divided by the limit of 1 minus z, k goes to infinity. Why is that true? That's what this says. Remember, another way to write all of these arrows is as limits. So that's what I'm doing. First we've got a ratio. Ratio converges to that. LM. What I know L is, what I know is M is, well, those are the limits. That's how you can write those down. And there's a subtraction, and there's a difference. That's what I'm doing here. So first I have the limit of the top divided by the limit of the bottom is the limit of the quotient. And then I have the limit of the left-hand side minus the limit of the right-hand side of the expression of the numerator must be the limit of the numerator. What is this equal to? Well, if the modulus of this is 1, then this is equal to 1 minus 0 over 1 minus z equals 1 over 1 minus z. If the modulus is greater than 1, then this is diverging to infinity, and the limit will be infinity, because we consider these things to be the same in our definitions. This is an extremely important definition. I really should have said, oh boy, here I go defining things again, because this has been quite a sequence of them for you. A sequence. Is a Cauchy sequence. Sometimes just is Cauchy if for all epsilon greater than 0 there exists a natural number in the integers, so that S of m is less than Sn, which is less than epsilon, for all m and n greater than n. I'm going to rewrite that. I like to have all the quantifiers up front. For all epsilon greater than 0, there exists an n in the integers, so that for all m and n greater than or equal to n, Sm minus Sn less than epsilon. Strictly. In other words, this is saying that when you consider elements of the sequence that are very far progressed along the sequence, the difference of their distance must be less than epsilon, which means they're converging to some point. They're getting very small. They must be converging, and that's the statement of this next theorem. a sequence is convergent if and only if it is Cauchy. Proof. The proof in the book basically says split the sequence into two real sequences, show that the real sequences are Cauchy, use the real result that implies a limit point, implies a limit, combine limits to get the complex limit. All that's well and good and fine as long as you know that real Cauchy sequences are guaranteed to have a limit. The proof itself is not really, in the complex numbers directly, is not really any more difficult, except instead of dealing with open intervals, you're dealing with open balls. I suggest you prove it. It's a good application of the, I'll do it for you. Okay, so I haven't written down notes on this. This is just going to be straight off the top of my head. I'm really hoping I remember this properly. Otherwise, I will just have to cut the video. You'll never get to see the mistake. So yeah. Okay, so let's say SK converges to L. We need to show that it's Cauchy. So let's take SM minus SN, and we're going to telescope the series. So this is SM minus L plus L minus SM, and this is less than or equal to SM minus L plus SN minus L. Okay, and because it's convergent means that for all epsilon greater than 0, there exists some element of the natural numbers, so that for all k bigger than n, sk minus L is less than epsilon. So I'm going to choose epsilon over a half, whatever that is, and then if m and n are bigger than n for epsilon over a half, then sm minus sn is going to be less than, well, that is less than epsilon half, and that is less than epsilon half, so this is less than epsilon. Bingo, it's Cauchy. Tick one direction. So suppose sequence is Cauchy. I'm going to do a proof by contradiction. Suppose for all L inside the complex numbers, L is not a limit point. Okay. If L was a limit point, then for all epsilon greater than 0, there would exist some n inside the natural numbers, so that for all k bigger than n, that would imply that sk minus L was less than epsilon. I need the opposite of this, right? That means that there exists an epsilon greater than 0, so that for all n in the natural numbers, there exists a k bigger than n, so that S of k minus L is greater than epsilon. Right. So now how do I prove this? Sm minus Sn, that's the quantity I want to consider, and I know that this is less than Sm minus L plus Sn minus L, and I need to show that this thing is less than epsilon for all epsilon that I choose. So I might as well pick this epsilon. I'm going to call this epsilon epsilon L. And M and N can be arbitrary, right? So right. Choose. What's the definition of Cauchy? Definition of Cauchy is we want to find a contradiction with the statement that for all epsilon greater than 0, there exists a natural number inside the real numbers, so that for all m and n greater than that, we have Sm minus Sn is less than epsilon. Now I have a particular epsilon in mind, which is that one. So in particular, epsilon L is greater than 0, so there exists some n, epsilon greater than L, because we know the sequence is Cauchy, so we know this is true. So there exists some n, so that for all m and n greater than n, Sm minus Sn is less than epsilon L. Okay, well that's good. But here I know that for all n there exists a k, so that's true. Also, there exists, and I'm just going to say nl, also there exists k greater than n, so that so is L, is Sm, is Sn. The distance between them is less than S, and then we have Sk over here, and Sk is larger than n. So in particular, I know that, so if let's say I pick n to be equal to k, then this implies that Sm minus Sk is less than epsilon L. Can you see the contradiction coming? Maybe. No. Sm minus L minus Sk minus L is less than or equal to Sm minus L minus Sk plus L, which is equal to Sm minus Sk. Now you should see the contradiction coming. What's that? I don't know what that is. What's this? I do know what that is. That's big. So this is Sm minus L let me write this down. Well, that's less than, so we have Sm minus L minus Sk minus L is less than or equal to that, and that is less than or equal to epsilon L. So Sm minus L, it also happens to be bigger than epsilon L. So this is minus epsilon L plus sk minus L. Right, what's that? We know that sk minus L is bigger than or equal to that. So 0 is bigger than or equal to epsilon L minus sk minus L. And that implies that Sm minus L is less than or equal to 0. Well, that's a problem. That's a problem. So either Sm is equal to L, or this term is negative. And that's an issue. And if Sm is equal to L, then remember how we had this? Sm minus Sn is less than epsilon for n greater than n, and I picked n to be equal to k. So this statement here, if Sm was equal to L, would convert to L minus Sk is less than epsilon L. But that's a contradiction, because by assumption, I know that Sk minus L is bigger than or equal to epsilon k. And that's my contradiction, which finishes the proof. Okay, so that was a little long and involved. I had to think things through. It's probably good for you to see actually what an unprepared proof looks like when I'm trying to put all the definitions together and work it out. Think how the definitions fit and work together. Why is it good to see? Mathematics that you see in a lecture has already been prepared, thought about, and polished, looked at, cared about. You get to see the polished, presented version, the perfect bit. Which, to be honest, is not what maths is. Maths is a lot more like that, where you think about things, put the ideas together, play with them slightly. Right, and I think that's the end of section 2.4.